Dear all, this is Chen Wen presenting NoStop, a novel configuration optimization scheme for Spark streaming. Here is the outline of this presentation. Firstly, let's start with introduction and motivation. An increasing number of big data applications in various domains generates datasets continuously, which must be processed for various purposes in a timely manner. As one of the most popular systems for streaming data processing, as shown in this slide, Spark Streaming applies a batch-based interval which receives real-time input data streams and split data into multiple batches, each of which is processed by Spark engine as a regular Spark job. System stability and end-to-end latency are among the utmost important performance metrics for streaming data processing. System stability is generally considered as the bottom line for streaming data processing. If the system fails to process data as fast as they arrive, the data may accumulate at the input data queue, hence leading to possible data loss or system failure eventually. End-to-end latency denotes the duration from the time when a system receives a data entry to the time when a corresponding output is produced. Obviously, such latency reflects the system's capability of providing real-time results for fast user response. Therefore, in this paper, for a given Spark streaming application with a fluctuating input data rate, our goal is to dynamically and adaptively determine the most suitable system configuration to achieve minimal end-to-end latency while maintaining system stability. Research has been conducted to improve Spark streaming application performance in distributed environments. However, most of the existing efforts for performance optimization of Spark streaming consider cases that require a constant input data rate, which is very rare in real life, or they require the ability to scale up cluster resources on demand, which is almost infeasible in non-cloud environment. Some efforts apply machine learning-based approaches, which require a sufficient amount of historical data for training. Different from the aforementioned work, we propose a stochastic approximation-based streaming optimization scheme to minimize end-to-end delay while keeping the system robust to varying input data rates. Compared with machine learning-based approaches, the scheme requires no historical data and incurs negligible computing overhead. Next is the problem statement. Before we directly jump into it, I'd like to illustrate the relationship between batch interval and batch processing time. Maintaining system stability and minimizing end-to-end delay are closely related and are reflective of the relationship between batch interval and batch processing time. When batch interval is smaller than batch processing time, the unprocessed batch would pile up in the batch queue. This system is therefore unstable and would even crash with long-running applications. When batch interval is greater than batch processing time, the system is stable because the batches are retrieved from batch queue and are processed immediately. However, Spark engine would sit idle waiting for batches to arrive, hence resulting in a long end-to-end delay. When batch interval equals to batch processing time, this is the ideal situation where there is no data accumulation in the input data queue. Hence, the system is stable and there is no idle time for the use of computing resources. However, this situation rarely happens because of the complex system dynamics, data rate variation, and resource sharing complexity. Minimizing end-to-end delay while maintaining system stability is equivalent to minimizing batch interval under constraint that the batch interval is no less than batch processing time. So here comes the problem description. Given a Spark streaming application executed in a distributed computing environment and an input data stream arriving at a varying speed, we wish to find a proper setting for batch interval and the number of executors in real time to achieve minimum end-to-end delay, while subject to the constraint that the system is stable. Next comes the design of NoStop. The main goal of NoStop is to achieve low end-to-end latency and while maintaining system stability. Meanwhile, we also consider the following properties of NoStop. Firstly, we hope it has noise tolerance. It is well recognized that randomness exists in the dynamics of streaming data processing in distributed environment, including network jitters, resource contentions, etc. One salient feature of NoStop is to explicitly account for such randomness. Secondly, generality. We hope it is applicable to different types of Spark streaming applications executed in different computing environments. For example, heterogeneous or homogeneous cluster or cloud-based cluster, etc. Thirdly, efficiency. We hope it converges to minimum end-to-end delay promptly for fluctuating input data rate with negligible overhead. Lastly, and most importantly, we hope it has performance guarantee. That means it would provide a theoretically proved performance bound. This slide shows the architecture of NoStop. Spark streaming receives input data streams from multiple channels for processing and output data to HDFS for storage or other databases for management. We designed Spark streaming listener to report real-time system status to NoStop. Based on each newly updated performance vector, NoStop computes the next step configuration parameters and make a real-time adjustment to the system configuration. We use simultaneously perturbation stochastic approximation based approach algorithm to accelerate the process of finding the most suitable configuration. The rationale behind the use of SPSA is listed as follows. Firstly, it does not require an explicit analytical form of end-to-end latency. It treats the execution of Spark application as a black box, where the input is a set of control parameters and the output is end-to-end delay. Secondly, it does not require any additional information about system dynamics, applications, and input distribution. Thirdly, since it requires only two measurements of the objective function, regardless of the dimension of control parameters, so it has the benefit of low time complexity and does not require a large amount of historical data. Lastly, its performance is theoretically guaranteed. Here is the detail of SPSA-based optimization algorithm. Let theta denotes the control parameters. G theta denotes the end-to-end latency. The standard stochastic approximation form is given by the following equation, where theta k is the set of control parameter values in kth iteration. AK is a non-negative gain coefficient. G theta k is the simultaneous perturbation estimate of the end-to-end latency gradient, and it's calculated as the following equation, where theta k is a random perturbation vector, and ck is a positive coefficient. With SPSA approach for our problem, when k approximates infinity, we are guaranteed by theory that we would find the most suitable configuration setting where the end-to-end delay is minimized. For performance evaluation, we set up a heterogeneous cluster consisting of 5 computing nodes. where Apache Hadoop, Apache Spark, and Apache Kafka are installed on them. As shown in the figure, 4 workloads with varying input data rate are considered, namely logistic regression, linear regression, word count, and log analysis. These figures, here comes the experiment result. These 4 figures show the optimization evolution process for these 4 workloads. The y-axis is the normalized time, and x is the iteration steps. As iteration evolves, we can see clearly that the blue line, which represents end-to-end delay, decreases while maintaining stability. We also compared our results with default setting and the Bayesian optimization. This figure shows performance improvement over initial configuration set by default. These results illustrate that NoStop significantly reduced end-to-end delay in comparison with the system's default configuration. And these 2 figures are the comparison between SPSA and the Bayesian optimization. The final optimization results are comparable, but the search time and iteration steps of SPSA are less than that of a Bayesian optimization, which clearly illustrate the runtime efficiency of NoStop. Thank you for listening to my presentation.